Hello, my name is Rick Poe. I'm an airline transport pilot, and I'm here with Operation Aviation. And one of the philosophy items I want to provide in this Gen Fam is to create a bridge between the flight operations and the maintenance side of the house. And in doing so, give you a perspective from my view as a pilot and interface with the mechanics out there. So how I want to do this, I just want to start from a broad view where we are with the Airbus. Now, for those of you who are not familiar with the Airbus and have worked on a lot of generic type of aircraft, basically the cable systems, the Airbus itself is a computer. Think of it as a flying computer. It's electric and it does have hydraulics, but it is also interfaced with a lot of data, and that goes into several computers on this aircraft. Now, to look at this, it is a fly-by-wire aircraft. What is fly-by-wire? Essentially, I send a signal from one input and it has a receiver at the other end. Let's say I put a control input into my stick for an aileron movement. Well, the receiver at the other end, at the aileron servo unit, picks that up, sends a signal to a hydromechanical unit, and positions the aileron. Now, with this said, this airplane has a logical system to it, and we classified in three categories: normal, alternate, and direct. And essentially in the normal, just think of yourself as human, everything working, breathing machine. The alternate is that, say we tie your hands up, now you have alternate means of movement, bypassing your hands. And then we have direct. This goes directly, ironically speaking, to the stick and rudder. But again, this airplane is an electric, hydraulic airplane. There is only one, or basically two cable systems that move this airplane, and that is what we call the THS, which is the elevator, and the rudder system. Just as a side note, that you'll notice that some of the other new Boeing aircraft, they are coming up to speed as an electric airplane. However, the Airbus itself is the first forerunner of a completely different airplane. And one of the critical items on this, just to get into what I would call the nuts and bolts of this, is the initial wake-up. When power is first supplied to this Airbus, we have a flight warning computer system. And think of yourself when you go and turn on the computer. You turn it on, does one start entering a lot of data and hitting buttons? No. You let it boot up. Well, essentially the aircraft operates in the same principle. You give it about a 45-second time frame, it does a self-diagnostic, and it's up and running. These are some of the particulars that you'll be more coming across when you encounter this Airbus. Appreciate you all coming to this course. Looking forward to speaking with you again.
We are now on to flight controls. We just heard from Rick, giving you kind of a broad view of the flight controls for the Airbus A320 family. This particular topic is going to be broken up into two sessions only. So we have session 1 and session 2. Session 1 is going to be additional overview. I know that Rick kind of gave you again some things to be aware of when it comes to Airbus. It's a big flying computer when you compare it to some other ones in general. It's probably the most computerized at this point. But in addition to the overview, including byte menus, which we're going to cover in session 1, we're going to go over the primary flight controls computer systems. And that's the heart of everything as far as the data that gets processed and calculated essentially in order to basically have a fly-by-wire situation that we do have with the Airbus. So let's go ahead and give you, I just want to give you an overview of the, what we have, what we're talking about here with flight controls when it comes to the Airbus. You have just a reminder, just a review for you all. The primary flight controls are AER. Okay, that's your ailerons, your elevators, and your rudder. And then when we talk about the flaps and slats, those are your secondary or your control surfaces. So we're going to be getting into that as well. But I just wanted to get a review in your mind. Okay, AER, we got ailerons, your elevators, and rudder. Okay, so that's what we're going to be talking about when we talk about these control computers in session 1. And then when we get to session 2, we're going to be looking at the slats and flaps control computers. So we have those and kind of how they're going to interact with the power control units and signals that are coming in, etc. We're going to have pickoff units that exist here along with transmission systems and asymmetry position, etc. Because remember, obviously it's measuring and picking up, monitoring the positions, of those components. So we'll talk about that, and also, of course, getting into the maintenance, because there's just kind of a, like I say, level 1 maintenance, and there's like deeper maintenance where they can really get into it based on the data that's collected. And we'll talk about concentrators, because that's one of the components with the computerized system, is being able to gather a lot of data and being able to present fault signals that are going to be helpful to the maintenance technician. So that's just kind of a broad view what we're going to be covering. Primary flight controls, of course we're talking about the ailerons and the rudder and the elevators. And think of this in a kind of the broad stroke is an electrical system, because Rick mentioned about this being an electrical airplane. It's kind of funny when we think about how things started, years ago, decades ago. We talk about, things starting off mechanically and then getting the electrical part along with that, and using hydraulics, of course, with that. But, essentially, we've moved into this direction with having things run electrically. And this is all because we have these computers that are enabling, a more streamlined power system for operating the flight controls. So with here, there's the ELACs. I'm going to just kind of give you, in general what we have here. The ELAC systems, those are your elevator and aileron computers, and there's 2 of them. So if you ever get tested on, if you ever see that as a test question, how many ELACs are on the Airbus, there's 2. Okay, and I'm talking about the A320 family. When we start getting into higher models, things are going to change. We're going to see some differences here. But right now, there's 2 ELACs. You have 3 SACs. Those are for your spoiler elevator. That's your spoiler elevator computer system. There's 2 FCDs, and then we also have your data concentrators and 4 accelerometers. Okay, so all those, what I just mentioned right now, those control computers are responsible for maintaining the balance with the primary flight controls. Now, they're redundant systems, so with ELACs, even though it's designated to operate in normal mode for elevator or ailerons, if for some reason there's a problem with the spoiler and elevator, it's able to kind of pick up on that when it's in standby mode. So just know that those control computers operate that way, where they're able to work in conjunction with one another in order to make sure that the plane is flying at the desired level. The FCDCs, if you're not familiar with that, and it's the first time hearing it, that's your flight control data concentrator. And so these components, I should say the software or hardware, is actually receiving failure signals, okay, from different sensors, and you have that data going there, and it's detecting, of course, and it's also identifying, not just detecting faults, but it's also identifying what those faults are. And then we're talking about isolating, because what's it trying to do? We got to protect the system from any faults, because we don't want to have a domino effect. So it's going to isolate that, and that's what it does. And it's going to send those signals to the ECAM and the CFDU, okay, in the flight compartment. Okay, and so, you know, with that, the data concentrator not only is it receiving those fault signals, but it actually retransmits that contact information, the failure context information, you know, back to the SECs and the ELACs. Okay, so it's kind of an interesting flow, and I'm giving you kind of a broad stroke, but that's how that works. And just kind of a side note, or, you know, to kind of think of it this way on the side, is if you have multiple failures, that's like the same kind of failure, then it's only going to show one message. You're not going to have like 5 messages on the same failure. It'll just show up as one. The exception to that is the accelerometers. If you have a failure with one of them, or excuse me, if you have a failure with 2 of them, you're only, you know, you're going to actually have 2 separate messages, whereas in any other components you're going to have, you know, just the one message. So, you know, that's what we have to say about that. There's also the hydraulic part of this. So when you talk about the flight controls, control computers, you know, that's part of the electrical flight control system. And then we also have the hydraulic part of this. So as far as our power supplies for the computers, we've got, you know, or for the operation of the flight controls, you know, we've got electrical and hydraulic going on. And just kind of a thing that, just reiterating what Rick had mentioned before, is about, you know, why, my goodness, we just mentioned electrical and hydraulic. What else do we have? You know, I mean, besides pneumatic, but we're talking, you know, that's not what we're talking about here. We're talking about mechanical, right? Because a lot of things are, you know, still running on mechanical, and I'm not going to name the plane. I think you guys know. But I guess what I'm trying to say is that here, minimal, okay? There's 2 sets of cables, and that's pretty much it. And we're talking about that when we get to the trimmable horizontal stabilizer system. So that's when we have that, and as well as the rudder pedals. That's mechanical. All right. Then we're going to get into speed brakes, because speed brake, as well as when we talk about the spoilers, is going to be in relation to the ailerons, because they work in conjunction, you know, with one another to have the pitch and the roll control, right? So that's why, even though, you know, spoilers are not considered primary flight controls, I'm going to be mentioning that, you know, when I'm talking about in session 1, because, you know, again, they work in conjunction with one another in order to have that control. So you'll hear that. And then we have, of course, servo controls, and we're going to look at the maintenance with that. And, you know, then we'll get into, you know, the rudder and all that. So let's just kind of start with our, you know, primaries, just to, again, just kind of reorient yourself with this. But ailerons are for the roll control, you know, rudder is for yaw control, and of course you have your pitch control, so you have lateral control. But the spoilers, you know, a mirror image on each side. Each wing is going to have your 5 surfaces, so 1, 2, 3, 4, 5 on the one wing, starting inboard, okay, and then on the other side, inboard starting at inboard, 1, 2, 3, 4, 5. So you have a mirror image, you know, on the other side. So, you know, when we talk about the spoilers, we have the function of, you know, ground spoilers, and that's for all the surfaces. And then your speed brakes are related to 2 through 4, you know, as far as, you know, the spoilers involved with that. And your roll spoilers are 2 through 5. Okay, surfaces there, you have side stick controllers that are controlling those surfaces, and then you do have that speed brake control lever that you can operate, you know, a pilot can operate, or there's an automatic, you know, you can do it automatically in autopilot. Okay, so that's spoilers and the ailerons, of course. You have the roll control there, and then you have kind of an aileron that's augmented by the 4 spoilers on each of the wings. The rudder, okay, that's for yaw control, and with this one you have 3 servo controls. So there's 3 of them. One has to do with the rudder. You do, of course, have manual input, which you can have with the, you know, pilot has that option with the rudder pedals, and also you have the stick controller for the rudder as well. Now the elevators, those are mechanically independent elevators. You can control them with the side stick controllers, or it can be an automatic phase there. Okay. All right, so let's kind of start with the first control. And remember, I said there's 2 ELACs, 3 SECs, 2 FCDs, you got 4 accelerometers. So let's start with the ELAC system. Okay, remember there's 2 of them. So the ELAC system, it's just short for elevator and aileron computer. And so obviously its primary job is to control the elevators and ailerons and making sure that things are positioned right there. And also the THS positioning, okay, your trimmable horizontal stabilizer. So each of the, again, there's 2 of them. And the computers have 2 units involved. There's a MON and a COM unit. And so your MON is going to be checking to make sure that the orders are correctly executed. Okay, like after it's been executed, did it do it right? On the COM unit, it's going to be calculating the deflection that's going on and making sure, as a function, it's going to be doing that as a function that receives signals, that input, and is in making sure that it's going to, make that command to move the surfaces. Where these are located, okay, the ELAC 1 is on the 80 is on the 80 VU panel, so you got 83 and 84 are located on that 80 VU panel. Okay, that's for both the ELACs. Now, what about the SECs? Okay, you've got spoiler and elevator computer. That's what SEC stands for, SEC system. So remember, these are electrical, under the electrical system, and SEC obviously is going to control the spoiler, and the elevator. And the elevator, that's what it's doing, because you have ELAC system that's controlling the elevator and aileron, and then you also have SEC that's controlling the elevator. But in addition to that, you've got the spoilers being controlled by that. So here, there's 3 of them, and it's, the SEC is going to be receiving inputs, and inputs that are going to go into the movements of those surfaces. So it's going to be responsible for, controlling the roll, the speed brakes, and of course the THS controls your elevator and the ground spoilers. And these are located, the SECs are there's 3 of them, okay? And so 2 of them are located on the 80 panel, and then the other one's on a 90 VU panel. Now, what about the FCDs? I'm talking about the I'm talking about the flight control data concentrators, so the FCDC. Okay, FCDC is here, and what does it do? Okay, it's going to be receiving data, and it's going to get that, it's going to concentrate it, and then what? It's going to be able to identify what's going on. It's going to detect them, for one, and then it's going to identify what it is, what are those failure signals, and then it's going to isolate. Okay, so when that happens, it's going to be looking for position and availability, and of course, like I said, failure signals. And what it's going to do is it's going to send, basically cause illumination of the lights that are indicating the priority between the side sticks. Okay, so side stick priority, and Rick can tell you about that, but basically being able to have priority, one over another stick in the flight compartment. Okay, so the FCDs occur, then you have all that transmitted to the CFDU, okay, your centralized fault display unit, and then that FCDC, okay, that was receiving those failure signals and gathering data about the position and availability of those flight control surfaces, is going to retransmit back to the SECs and the ELACs that information that was there. Okay, so that's what that data concentration, concentrator is there for. Now, just some things to be aware of, and I'm going to get into byte here in a little bit, but your byte tests, you've got automatic tests and you got periodic tests, and so those are actually performed by this data concentrator. That's why I'm bringing it up right now. So we've got those done by that. And actually, since we're I know I'm not really sidetracking, it's related because I'm talking about the data concentrator. So with with the data concentrator, running the periodic tests, just to kind of give you an idea on the different kinds of tests and troubleshooting that goes on. You have the test for, basically your servo control damping test and for your aileron and for your elevator. Those are your periodic tests. And those are set, kind of launched by the CFDIU. All right, and that's going to go through the MICDU, okay, your multi-purpose control and display unit. Okay, so just wanted to mention about the periodic tests, since we're talking about the concentrator and how it's performing those periodic tests. But the other thing too, remember I mentioned that if you have two accelerometers failing, it's going to show as two separate messages, okay, two separate fail messages. If there's other failures that are going on and they're the same, they're just kind of the same kind, then it's just going to show the one message. Okay, and the FCDC, your concentrator, is also, again, it's going to run even more tests. So you've got not just the periodic tests that I mentioned, but you have integrated test functions that are going to be able to detect those failures and identify what they are, and also just to isolate in order to protect and not have that domino effect, and being able to have success with control of those flight control surfaces. So so then, so anyway, you've got that, just so you know, with that concentrator. All right, and then of course you've got also, I mean, the whole idea with the ELACs and the 3 secs and whatnot, is that they're redundant. I mean, like I mentioned before, if one is in normal mode, but then in standby mode, it's going to be helping with control of the other parts, or other parts to it, as far as the flying. So also when it comes to installation, okay, I'm talking about the ELAC, okay, or anything in the flight control system, which is the ELACs and your SACs. You have specific connectors that are used for, within this flight control system that's electrical. Okay, you've got 2 routes. You've got Route 1 and Route 2. And you got one that's going to be powered from the emergency supply, and then you're just going to have one from normal. So those are the 2 routes. One coming from emergency and one coming just from a normal electrical supply. You also have control signals that are routed to 2 other routes. You've got M and S, and those are monitoring signals that are going. There's control signals going to S, monitoring signals are going to go to M. Kind of like monitoring is for M for monitoring. You can think of it that way. And then of course you also have a protection against lightning. Lightning's a threat to the aircraft, and it's electrical system, so of course you've got to have some fail safes there for that, and it has it. So it's kind of in the wiring, being able to have a way to ground it in case that there is an lightning strike. And there's a diagram that shows you kind of the way it goes from, remember I mentioned, on the wings you've got your flight control surfaces, your spoilers, and you got one, from inboard, your right wing, 1, 2, 3, 4, 5, inboard left wing, 1, 2, 3, 4, 5, so you got your mirror image. And you also need to kind of be aware of, what hydraulic systems are supplying power to which ones. So, of course, G is for green, Y is for yellow, B is for blue. So that way you'll know, okay, this should be coming from this hydraulic system, etc. The other thing too, if you notice, is where are they going to show up? You got ELACs are going to show up. Your ELACs are involved with that, and then you're also your SACs, kind of just showing that on the diagram. You can see interface with the rudder pedals. Okay, your FAC 1 and FAC 2, are supplying, you got inputs there in order to have the hydraulic power, be applied, in the rudder system. Okay, so then I want to talk a little bit about control laws. and we're gonna have commentaries. That's our that job is to, have as much information as we can give you. And so we're gonna have some commentaries by Rick, and also probably some from an aircraft maintenance technician. Rick Poe is a commercial airline pilot. Has been doing this for 30 some years, and has talked to aircraft mechanics. So he's not, he knows about some maintenance, okay, so he's not completely oblivious to that reality. But one of the things I wanted to mention is he can tell you a lot about control laws, and really, how is this affecting what we talk about maintenance and whatnot. There's a kind of a matrix as well that lets you know what's controlling what. These are control computers. You guys who are avionics technicians, this is where you want to have a heightened awareness about. But control laws, there's 3 of them. You've got your normal, your alternate, and direct. Direct, that means there's no intermediary. You do not have anything as a interface to get information from point A to point B. It's direct input. An example of that will be your rudder pedals. Okay, so kind of just going to go over some of them, maybe not all of them, but let's just kind of go over. Let's kind of start, since I mentioned the rudder. I mean, for yaw control. So you get alternate yaw control, okay, because you've got direct control of the rudder from the pedals. Okay, you can also get that from the trim switches that are complemented by a Dutch roll damping function. You've got damping function there as well. So then you have your pitch normal law. That's combined control of the elevators and your THS that are coming from the stick, your sticks, stick controllers. And of course you got priority logic involved there because you have 2 sticks. One takes control, one doesn't, etc. Okay. Now that's normal law, where you have just kind of like normal ops. Okay, and I'll talk about limits in a little bit, because we'll get into, from a maintenance standpoint, kind of when we talk about things being, what's the operation that can be done up to a certain knots, because greater than that, then we can't do it. So here, as far as the pitch normal law, we have a protection that's involved here, and that's the high angle of attack protection. Because you don't want to, and that's what I was talking about right now, is that you don't want to have too high an angle of attack, right? Otherwise you're going to have a stall issue. I mean, that's what pilots don't want to have. So there's the other threat too that I'll get into. But that's definitely one thing, is the high angle of attack. It needs to keep within a certain level, limit, if you will. Okay, so then when you're talking about, pitch normal law, if we're talking that was in flight, if we have on the ground, then normal law is providing that fixed relationship between the stick control, right, and also the elevator deflections, because that has to do with pitch. Okay, your alternate law, as far as that goes, you have limited authority load factor. You have your pitch rate feedbacks. Okay, so you've got that load factor limitation, which you still have with the pitch normal law, but it's limited, and that's kind of what I guess my point is. You got normal ops, and then when you're an alternate ops or an alternate law, you've got some limitations. And of course, pitch direct, you've got the control of the elevator angle from the side stick controllers. And then of course you have a mechanical control of the THS. Okay, I'm not going over all the laws, but there's a matrix if you're interested in looking at that. We can get that to you. Okay, so remember what I said about, this is an electrical system. So, the ELACs, your SACs, your data concentrators need to have an electrical supply, So with the way it's broken out, you've got the ELAC 1 and SEC 1. So, we could say ELAC 1 and ELAC 2 are supplied by, X bus, whatever it is, but that's not how it is configured. So X that in your mind, okay? Because as what I'm about ready to tell you, ELAC 1 and SEC 1, because we have SEC 1, SEC 2, and SEC 3. We have ELAC 1 and ELAC 2. And ELAC 1 and SEC 1, those together are supplied by the same electrical power source. And that would be your buses. We're going to, these are going to be by buses. You got an essential bus bar and DC supply that is supplying power for the ELAC 1 and SEC 1. Now, for SEC 2, okay, so that was ELAC 1 and SEC 1. And then if we move on to SEC 2 and SEC 3, and we're going to talk, throw in the THS electrical motor 3 and also your data concentrator 2. Those are all supplied by the same normal bus bar. So that's a group. Okay, and then what about then the THS electrical motor 2? That stands alone as far as it's receiving power from an essential bus bar. And just follow your maintenance manual as far as the location of those bus bars and their identifiers. Okay, I'm not going to mention that. Things can change. So remember, keep in mind too that we're not talking about an old DC-9. We're not talking about the Boeing original series where things are just what you see is kind of what you get. When we're talking about computers, we're talking about very frequent change, because computer technology just seems to keep going and going. It doesn't stop, and it's going at a really high rate. So I say that because the way that the evolution continues with development into these models and putting the computers in there, it's going streamlined. So as we get better at being able to collect data in a very small piece of equipment, piece of a component, then we're going to have it maybe in a different location on the airplane. So keep that in mind. The Airbus it's a flying computer, and next year, 2 years from now, it may not be in the same place. They might have changed the footprint of it, and then it used to be whatever, like a 4x4 or whatever, but now it's a 2x2. Just kind of an example. So kind of just really keep that in mind. We're definitely in an age of computers, so we see the application here on the aircraft. Of course, you got data concentrator also supplied. All these are supplied by either an essential or a normal bus bar. Okay, you also have a hydraulic power supply. Remember, we had 3 hydraulic systems, the green, yellow, and blue systems in our bus, and they're all playing a part in making sure that the flight controls are able to be controlled by the pilots, essentially, right? Because we want to make sure if one fails, we got 2 others, and we want to have that nice, I was going to say kind of like a circus, but just kind of things going in a nice, smooth orchestra, if you will, of providing that power as needed. So you have these redundancies, obviously, and you have, at least if we have 2, let's say we have 2 hydraulic systems that go down, then we at least have the one that's left to operate, within a certain envelope, a flight envelope, for safety and bringing the plane down, etc., and making sure the electrical power is there. I have to have electrical power, or we just won't have those control computers. That would be a bad deal. You fry the APU, that's a bad thing. Okay, that's your backup, and so that we wouldn't want that to happen. But okay, so we've got hydraulic characteristics here, of the flight control components. And of course, when we talk about hydraulics, you guys already hopefully already listened to the hydraulic lesson. Is hydraulics, you have valves. We talked about the leak measurement valves. We want to make sure, obviously, that there's no leakage in the hydraulic system, because flight controls rely on hydraulic fluid to be there, which has to do with pressure and getting that power to the flight controls. So priority valves, okay, those are going to be upstream, and you're going to find those in your blue, green, and your yellow systems. Okay, your green systems, you're going to find them upstream of your flap and slat PCU motors, and your yellow system, it's going to be upstream of your flat PCU motor, and then your blue system is going to be where the priority valves are upstream of the slat power control unit motor. Okay, so what so that's nice that we have those there, being able to have those priority valves. Okay, and with the priority valves, we have, we need those there because we don't want to have, something dropping below a certain pressure when we need to have them for certain user systems, and especially when they're operated at the same time. We want to make sure there's availability of it. Now, your leakage measurement valves, I mentioned those before when we talk about just when we're on hydraulics, but here it's just being able to monitor those leakages. Of course, any leakage is a bad thing, but there are different degrees of it. And so you have valve blocks that are installed in the supply lines, okay, in order to measure the internal leaks that may be going on in that whole system. Okay, and of course you have a safety valve. Safety valves also installed, but in the green system's your main there, so your green system, and again that's there in case you don't want to have an engine hydraulic system problem, like blowing out. So so you have that. Okay, and just kind of giving you just an idea with the primary flight controls, your ELACs, your SACs, your concentrators, okay, your data concentrators. Now I want to go into the physical part. That was software and hardware, but I want to go into now. Remember I mentioned the side stick controllers. You have two, one captain and first officer. So you got your side stick controllers used for your pitch and roll. This is your manual control. You have one for captain's side and one for first officer, and those are connected. So if you've ever, if you've taken jam fans for 737, we talk about priority. We talk about how you have a disengage, or being able to have one take over the other in case there's a failure of the one. Here you have a connection. They are electrically connected, and so, but you have to have one in control, if you will, right? So what is this doing here? We've got we've got a fail-safe concept with the two sticks, that if we have a problem going on, then we're gonna have a provision, okay, for neither the total loss of artificial fuel, because we want to make sure that they have that, or not having an undetected uncontrolled pilot order. I want to make sure we have that. You have, as far as the side stick and the characteristics of it, you have a protection boot, of course the hand grip. You've got two springs for that artificial fuel, two spring rods. Okay, so you've got the rods, the springs, you've got transducer units. There's one for the roll, one for the pitch. And then you also have two axes, and you've got a solenoid as well, because you have a solenoid in the AP mode. Okay, it's a higher threshold to move that side stick out of the 0 position. Okay, so a little bit on the transducer units. They're exactly the same. Okay, there's two of them. Remember I said there's two. And so they're exactly the same. And there's 4 sets of 3 plastic potentiometers that are fitted in each of those units. Okay, so 4 sets of 3 potentiometers for that. Now, there's a red light of the side stick priority. Okay, that comes on in front of the pilot who lost it. Okay, so red light means they have no priority, and so that's what comes on. The green light of the side stick priority. Okay, highlight that. Okay, the green light of the side stick priority comes on in front who has the priority. So that way they know who has priority. Okay, it's like who has control, right? If any of you have flown, and I'm on the helicopter side, so I'm doing the flights. You have 2 pilots, you're co-piloting somebody, you can't have both controlling, obviously, so right? So one has to say, okay, I have control. Okay, so that's, with this here, they have a light indication. The red light, they've lost it. Green light means that that particular pilot, where it shows in front of them, means that they actually have control. Then you can see on the diagram, kind of give me show you the panel where you have your master caution warning light or button, and that's where you have that side stick priority, where it's going to light up either red or green. Okay. You have control interface, because now remember I said there were 4 accelerometers. So here they're vertical acceleration values. And why is this important? You know, why are we even talking about, you know, accelerometer is just a measure of acceleration, okay? So what do those values, you know, have to do with anything? These are related to your pitch, okay? It's related to your pitch computation. So it's gathering these values in order to decide, because the computer's deciding, the computer's calculating and determining, okay, what, you know, with this input and this input, all these variables going on, what should it finally be? And then let me go ahead and make that correction. Let me make that happen. And that's the computer, okay? Computer's assessing all of that. And so it's taking these acceleration values into consideration. Just so you know where these are, the accelerometers, these are, remember, 4 of them. They are fitted in the fuselage. Okay, they're there, and they're receiving electrical power. Okay, or 28 volt, typical 28 volt DC, and then it's going to send out signals. So the accelerometer is sending out analog signals of that vertical acceleration, obviously reference to the aircraft body. So that's what it's doing, sending them out. And these outputs are connected to, remember I mentioned the MON and the COM, which are the like subunits of the ELACs and the SECs. And so it's going to send those messages to those subunits within the ELACs and SEC. And then you also have that force transducer unit, and that's going to measure, remember, force. Okay, it's going to be the pilot's forces that are applied to the rudder pedals. Okay, the rudder pedals. So that's what that force transducer unit is doing. It's measuring it. And so, all right, so you have that. And you also have the load cell. Okay, so what is that? The load cell is detecting the buckling of the rod that's generated by the loads applied to the rudder pedals. Okay, so load cell has to do with reading, you know, that load from the rudder pedals. And then of course from there, it's going to be able to send those signals to make it into a conversion on digital, and of course be sent over to your flight control data concentrator. Remember, just kind of everything concentrated to this data concentrator. Okay, so wanted to mention about the interfaces here. That's what they are. The other addition to that, we do have pressure switches. And I'm talking about hydraulic pressure switches. We're talking about hydraulic pressure. We've got 3 hydraulic systems that are participating in this whole, nice balance with providing, basically covering all bases to make sure that hydraulic power is available as needed on demand for the aircraft at any time. Remember, it's constantly changing as far as the demands when it's in flight. So you got 3 hydraulic pressure switches. All of them are the same. Okay, they're identical. I hesitate sometimes to say that, but if it's identical, it's identical. But always pay attention to, to the markings on parts when you're replacing them, obviously, because one may look exactly like the other one, but it's not, right, in some cases. So I just kind of an awareness here. I know it's like a little throwing this, a little bit here, but it's important. That's important to be aware of that. Your hydraulic pressure switches are going to be sending signals to your ELACs and your SECs, okay, about what's happening with the pressure in all 3 systems. Okay, now the switches, you have 2 parts. You have an electrical and a hydraulic part. Okay, so you got, on those switches, you have an hydraulically operated piston that's moving a diaphragm, and that's going to form the seal between the hydraulic and the electrical parts in there. There's also the switch assembly is also kind of configured so that's operating a switching element. That's just the way it's designed in order to detect, okay, and detect the pressure. Okay, so just, that's what we have on the interfaces. And then I don't want to be remiss in mentioning the speed brake. There's a speed brake control transducer unit. So, this is going to be the control for this. I'm talking about the speed brake control, is going to be coming from a unit that's on the aft left part of the center pedestal. Okay, that's where that's located. And so you have that. And the control lever, 0 position, it's locked in the maximum forward position. And then the lever is moved in an aft direction to extend. So aft makes the speed brakes extend. So that's the operational bit on that. Okay. And then also, of course, just, I already mentioned the about the transducer unit. So mentioned, just remember for a test question, because the load cell is going to be mentioned. Just heads up on that. All right. Okay, so let's talk a little bit about the control panel, because we want to be able to control the ailerons. And so with here, you've got ailerons in conjunction with spoilers in order to control the roll. So remember I said spoilers are not really the primary flight controls, they're secondary flight controls, but they work in conjunction with the primary. So here we got an aileron, ailerons operating at different speeds, and we have spoilers that are coming together. So we've got data that are coming into the control computers. So we're talking about for the ELACs and also for your SECs, okay? Because we have, the ailerons, for in ELAC, and spoilers are there with the SEC. So here you've got side stick controllers that are delivering those electrical signals, right? That are going to be computed and analyzed by the computers. And then you also have that artificial field system. That one is actually independent of the flight conditions. Okay, that's just so you know. Now with the ailerons, you've got 2 servo controls, that are hydraulically actuating the ailerons. And you've got the same thing for as far as operating the spoilers. All right. And then of course the positions are going to be indicated on the ECAM through the data concentrator. So remember I said data concentrator is sending those signals over to the ECAM and your CFDU. Okay. On the ground, just a kind of a side note, but plane on ground. Okay, if you don't have the hydraulic systems pressurized, then just typically, we tell people be careful, warning, make sure nobody's around, the equipment, the aircraft, when people are working on it, because when you have a loss of hydraulics, you can have those ailerons, droop down. In this case, they may or may not, but it's possible that they might. Okay. Autopilot, of course, you have interface with the autopilot system. It's kind of a given. Okay. And as far as your actuation, you have hydraulic actuation, and this is through the servo controls. Okay, remember there's 2 servo controls per aileron. So, gee, that might be a test question. Okay. How many servo controls do we have for each of the ailerons? That would be 2. And we have 4 fixed body servo controls. There's 2 per aileron that are interchangeable. So read your follow the aircraft maintenance manual, but remember I said I hate to say, oh, they're identical, oh gee, you can interchange, because some things you can interchange and some things you cannot. Here, typically, you've got the 4 servo controls, 2 for each aileron that are interchangeable. All right, so kind of let's see about the operation, because we want to look at, from a maintenance standpoint, what happens when you have an electrical failure, or what happens when you have a hydraulic failure, and what does normal look like? Well, normal things are functioning right, but what are we talking about here? So in operation, obviously you have the right amount of pressurization of the servo control in that's involving the opening of those pressure line closing valve, return line closing valve. Okay, so assuming that's all going right, everything's fine. But let's say that you have a problem with the electrical power. So then what happens is you're going to have a solenoid valve that gets de-energized, and the operation is the same to the one of servo control in the damping mode. Okay, because there's a damping mode situation here. With servo control in the damping mode, you're going to have the solenoid de-energized. That's what I'm saying about the solenoid valve. It's going to be de-energized, and then you're going to have the selector valve that moves under the action of its spring, of its own spring. And what's that going to do? Here's the chain of events. Then it's going to cause the chambers of the actuator to be connected through the damping orifice. Okay. And then you have the transducer identifies that change that's going on. So, with electrical failure, it's going to just follow that same process. In the hydraulics, you have closing valves are going to close, and it's going to isolate that servo control from the hydraulic system. If there happens to be a rupture in the return line, then you're going to have relief valves that holds that, fluid that's in there. It's going to hold it in the fluid reserve. Now we're talking about rigging facilities. Just so you know what's line replaceable, your servo valves, solenoid valves, and your linear. I didn't mention this before, but your LVDs. Okay, that's because we talk about transformers. I know I'm getting a little off beat here, or off the beaten's path, but I when I talk about electrical systems and I talk about transformers, we're talking about I talk about LVDs. Those are your linear variable differential. So you have those with transformers, as I just got reminded of that. But you also have this with the transducer. So LRUs are going to be your filter, servo valve. You've got your LVD transducer and your solenoid valves. Okay, so now what about the spoilers? Spoilers. This is all part. Remember, I mentioned about the spoilers kind of in a 1 through 5, starting inboard on right wing, inboard on left wing, going 1 through 5 to outboard. Just a mirror image. And so with this, what we have with the spoiler, we have, like I just described to you, it's just getting those signals again to the data concentrator, and then sending those out to the ELACs and SECs, and it's going to get information through that, and then it's going to retransmit it. So that's what you have with that. And just a thing on the spoilers. Obviously they're electrically controlled, and they're you got hydraulics to actuate them. And just so you know, as far as types, because there's different kinds of servo controls. In this particular case, there's 2 kinds or 2 types with here, and they're just different in their dimensions. So it's important. Just because they're servo controls, you can switch them out. That's not true. So please, kind of a heightened pay attention. And I can tell you, and Rick can tell you more, but on the Airbus, there's a lot of, I should say, kind of foolproof, if you will, where if it just won't go in, if you put it in the wrong way, it just won't work. It may seem like it's the same, but when you actually try to do it, it doesn't fit. So the only thing to do is flip it, turn it to the other side and put it in, and it fits like a puzzle. So I don't mean to simplify it, but it's designed that way. We're trying to obviously have the airplane to be safe and make sure that when we're installing things and removing components, that we keep mistakes to a very, very minimum. Okay. If you guys, and then there's some other information regarding, it's kind of a side a little bit, because probably some of you may or may not be interested in it, but There's an outboard type that's, the outboard one is larger. I'm talking about the servo control, is larger than the inboard one. And it's because of what its function is at the outboard. Okay, there's more load, so you've got, it needs to relieve more because of that, and that's why it's bigger. But just like a little side note there. Okay, so so just so you know, with the fixed body servo controls, and we're talking about with certain models, they may be interchangeable, but in some, if they're, you know, some may not be. So please just be very careful with this particular component and follow the AMM and visually inspect if you're handed parts, or you know, or you're choosing them yourself, whatever. Just make sure that you're getting what you should be installing, okay, properly. All right, so wow, okay. Didn't mean to go off on a tangent there, but it's related. I'm thinking about safety of the aircraft, and of course, making sure you guys have a little bit, have the awareness when you're doing all this. Okay. All right, and then so, of course, the servo controls the receiving the hydraulic power, right, from the 3 systems. So that's pretty much, again, this is all to control the spoilers. Okay. All right, so then let's kind of move on to, you've got a speed brake. I know I mentioned speed brake a little bit earlier, but you know, here you've got a speed brake function, and obviously remember the SECs and the ELECs are continuously monitoring. It's just like like I said, I call it an orchestra, but they're kind of just moving in sync with one another as far as, you know, making sure 24/7, you know, they're making sure things are running properly and functioning. And so the speed brake function is also being controlled and monitored by the SECs. And that's along with spoilers 2, 3, and 4 when we're talking about the speed brake function. So, you know, I wanted to be clear on that. We're talking about 2, 3, 4 in relation to speed brake function. Okay. So when we talk about the lever, because remember I said there's a speed brake lever. So with the speed brake lever, you have different positions and deflection angles, you know, when you put it in certain positions. So let's say you want it at full position, because that's one of the positions of the speed brake lever. So if you put it into full position, you're going to have a 57-degree deflection angle. Okay, just giving you, not that you have to memorize this, but I'm just letting you know, at full 57 degrees. If you have it in RET, you got 0. Okay, kind of retained at 0 degrees. Then you have a half. Okay, if you know, half position, then at 28.5. Okay, which is obviously half of 57. So you know, just kind of giving you orientation there. You have the speed brake. If you have some conditions, if there's certain conditions that exist, then you're not going to have the extension of the speed brakes. Otherwise, they're just going to retract automatically. So you know, so let's just give some examples. Okay, so what examples are, or what, you know, what conditions are examples where it's going to stop, you know, basically not allow the extension of the speed brake? Okay, well, one thing would be the elevator has a fault. Okay, so if the elevator has a fault, you're going to have 3 and 4. Okay, and I'm talking about spoilers. Okay, the spoilers 3 and 4 are going to be, they're not going to extend. So you've got Sec 1 and Sec 3. If both of those have faults, you're not going to have the extension of the speed brakes. Because remember, spoilers act as speed brakes. Okay, and then if you have the protection against angle of attack being too high, so you've got that protection, so the angle of attack doesn't go past a certain limit. If that's active, then you're not going to have that. Again, these are just, it kind of makes sense, you know. And also about the elevation, or excuse me, alpha floor. We'll talk about alpha lock in a little bit, but anyway, that's kind of interesting. So that's what's happening. You have those conditions, you're not going to have, you know, you're going to have those deployed, if you will. And if you look at the panel, you can see, you know, your ELAC and your SEC and your FAC. For on one side, you have ELAC 1, okay, ELAC, SEC, FAC 1, and then the other side, ELAC 2, SEC 2 and 3 in your FAC 2. Okay, so those are your VU panels 23 and 24, just for the record. 23 and 24, so remember that. So 23 VU, 24 VU, 23 VU has ELAC 1, SEC 1, FAC 1. Okay, for your indications there. And then on 24 VU panel, you have your 2s, okay, and your 3 for SEC, because you have SEC 2 and SEC 3 on that one. Okay, so operation a little bit on ground spoiler as we're talking about the speed brake lever. So when we have that speed brake lever in position, it's going to be affecting the spoilers. So we have, again, for ground spoilers as far as the operation of it. So the pilot's going to arm the ground spoilers because you can move the speed brake control lever up to the arm position. And then what's going to happen? Once it's armed, then those spoilers are going to automatically extend. And that's going to be during rejected takeoff. There's a certain threshold, so if you have speeds greater than 72 knots, that's one condition where you have that automatic extension, or at landing when you have both main landing gears at touchdown. Okay, kind of, and there's some, kind of pictures that kind of show you what's happening. Okay, all right, so a little bit more, just kind of on the servo controls. I mentioned to you earlier, there's certain inputs that you've got coming in that, okay, so for example, you have high pressure against the bypass valve. Okay, I mentioned about bypass valve and a plunger, so in a previous lesson, but you've got the bypass valve and then going to the plunger, which is going to close that valve. That's its mechanism. And then, of course, that means that the two actuator chambers those things are connected, or then become connected to the servo valve control lines. Okay. So the servo valve has a bias 0, and you've got a spoiler is at neutral as a result of that. So kind of a little bit, I don't get to major detail about it, but that's just causing that, when you have the spoiler at neutral, then it's held against that servo control stop. And it keeps it there, and then feeds the high pressure to the small chamber. And then that pressure from that area is applied to the piston rod. Okay. All right, and then there's a diagram of the servo control to give you an orientation of where they're all, what different parts are there. As far as your check valve, your closing valve, and your plunger that I mentioned earlier, and your crank lever, inhibiting valve, etc. See where those are located. Okay, and then just so you know, there is, there's a way to, obviously have manual movement of the spoiler panel, for maintenance, or deactivating it, and that's what that bypass valve is, maintenance bypass valve. It's like in many other applications. Okay. All right, and Rick is going to provide some information regarding as far as the conditions on spoilers. I'll just let him explain that. I certainly kind of want to give you conditions, because there's different conditions when we talk about the indication that we have for spoilers. So, for example, in condition 3, we'll have a spoiler that's represented as extended, and the symbol for that is in amber. It's an amber color. Just to give you an example on those different conditions. Of course, if there's a real big problem, just remember that X. And you see X on an ECAM, that's a bad sign. Okay. All right, so let's kind of move on to the rudder. Okay, that was talking about the spoilers and we got the speed brake. And now we got rudder, which has to do with your yaw control. So remember I said there's just kind of two places where you have some mechanical input, and you've got at the rudder and also your THS. So here you got rudder, your rudder surface that provides that yaw control. So, you know, mainly it's mechanical. You got the trim control that's electrically signaled, and then you've got artificial feel from a centering spring and rod. So, you know, and then you've got transducer units, you know, for the pedals that are going to send that data to your ELACs. You know, that's for the nose wheel steering system, by the way. Okay, so with the cables and all that, so kind of, I mean, cables are cables. When we come to rudders, you know, we're talking about the rudder pedals. We're talking cables. Remember, Rick was saying you got, you know, a couple of sets of cables. So with here, you've got a tension regulator that's maintaining that constant tension, and then the cables obviously are designed with enough flexibility, you know, for movement, etc., and just kind of, you know, basically helping with not having so much wear and tear on it. So they're pretty durable, you know, made with the kind of material that carbon's pretty strong, so that's what it's partly made of. Your rigging facilities, you get pedal stops, your rudder operational stops, rudder travel stops. So your operational stops, you have maximum input to the servo controls, and you have a travel limitation unit in there. Okay, it's your protection. So cables, you've got your push-pull rods as well. So it's pretty standard with those components regarding the mechanical control. And then your trim actuation is electrical. So, you know, you've got that actuator that's installed in the tail area that's going to drive a screw jack. Okay, so, you know, we got a moving part there. I can tell you, well, you guys probably already know, lubrication is very important. So, you know, we're talking about moving parts because that can be a domino effect to disaster, affecting the integrity of the structure of the aircraft. So we've had horror stories about that. Okay, so rudder trim actuation, you know, actuators manual controlled by the fax from the control panel. Okay. Okay, you do have rudder trim actuator as well. This is you have motors, so there's two of them. So with the rudder trim actuator, there's two motors for the actuator on this one, and they're installed on the same shaft together. So those motors that you have there, they're, you know, drives the output shafts. They're the torque limiter. You get the output shaft that's driving transducer units. Okay, so we have two motors, and then we have 4 inductive transducer units. Okay, and they're driving those. And then you also have on the control panel just kind of the reading, if you will, RUD, TRIM, so that's your rudder control. That's on the control panel. And you're also going to have a push button switch for reset, and you're going to have your control switch and an indicator for rudder trim. Okay, and remember I mentioned artificial feel, so you do have an artificial feel actuator. This is installed downstream of the cable quadrant. Okay, so you've got your, you know, you got a load spring rod, of course your screw jack that's going to hold it in place. So that's just the components related to your artificial feel. Okay, remember that I said there was a limiter. You know, you've got to have protection there. So with here, the rudder travel limiting system is just going to limit those inputs, right, to the servo controls. There's got to be a limit there somewhere with that travel of the rudder. Okay, and it's going to be, remember, servo control is like a little computer, so you got, you know, the changes there. It's going to be there to change that travel depending on what the airspeed is. Okay. When we talk, remember the FACs are involved. Your flight augmentation computers, by the way. That's going to be travel limitation unit, which is under that control of the FAC. So that's the FAC plays a part in rudder limiter, excuse me, travel limiter. Okay, so you do have that limitation unit related to the rudder. Okay, and then hydraulics, of course, you know, you got mechanical input, but you have hydraulic actuation of the rudder. Okay, and your position indicating, that's going to be obviously on the ECAM system. That's going to be transmitted to the SDAC through the position transducer. Okay, so it's that rudder travel, that rudder trim travel is going to show on the indicator. It's going to be a digital value on there. Okay, what about the yaw damper? Because we don't want to have too much yaw, so we have to have a damper actuation system here. Here you've got two actuators involving this function, and of course it's under the control of the FACs, which all of this is installed between the artificial feel and the trim unit, and also between that and the that and the travel limitation unit. So it's all, you know, close to there. And that's all going to be, you know, added to those of the pilots up to the maximum travel, right? And as far as like what, you know, what it's made of, I mean, what do we have with the servo actuator or the yaw damper? We've got two solenoid valves, you've got mode selector valves, a pressure switch, your servo valve, and a valve group. And you also have a piston with your LVT, remember I mentioned LVD, your linear variable differential transducer units, which you have here, that's isolated from the hydraulic fluid. Okay, and there's some modes to be aware of. You've got normal operation, so your yaw damper in the active mode, your solenoid valves are going to be energized in order to set the two selector valves to the active mode. Okay, so that's going to make that happen. In the bypass mode, that's your standby, they're going to be de-energized. And then you're going to have associated selector valves that are set to the bypass mode in that, you know, scenario. And then you also have hydraulic, let's, you know, obviously what happens when you have hydraulic failure, or what happens if you have electrical failure. If there's no hydraulic pressure, then the valves are set to the bypass mode. Okay, so then the switch is not activated. If there's not any electrical power, then, you know, your valves are going to be de-energized, and the operation is actually the same as bypass mode, the yaw damper in the bypass mode, because the solenoid valves are de-energized. You're going to have associated selector valves are going to be in the bypass mode. Okay, so that was the yaw damper actuator, and then we have the elevator. So let's talk a little bit about that. It's similar. I mean, when I talk about hydraulic actuation, it's the same operation, guys. Okay, it's the same. So I'm not going to go too much into it because it's just kind of a repeat. But you know, your elevator, you have two servo controls that are hydraulically actuate each elevator, right? The elevators. Here you've got two fixed body servo controls, and they're connected to the ELACs. Same thing here. You do have a damping mode. You also have a centering mode, okay, as well. So remember the different modes. You got active mode, there's a centering mode, and a damping mode. Just like I mentioned earlier about of course I was mentioning about the bypass mode in the last one. We're talking about the yaw damper actuation. But here we're talking about the elevator. Okay. Okay, and then what about the trimmable horizontal stabilizer, your THS? Okay, trimmable horizontal stabilizer. This is on the rear part of the fuselage. Okay, and that's in conjunction with pitch trim control. The elevators are obviously hinged. You get the 2 elevators are hinged on the THS. Okay. In this case, you have 3 electric motors, just to make sure. And this is again with the actuator, just to make sure that it's like redundant, if you will, but it's just to make sure that actuator is going to be functioning. And so again, under the control of the ELACs and the SACs. Of course, standby control isn't mechanical, so the pilot can override that by having a mechanical input, through the control wheels. And then there's an override mechanism that's used for that. So again, pilot can actually override that mechanically. And obviously mechanics, your mechanical side is what I described before with cable tension compensators and your rods, etc. Okay, and just kind of giving you just a broad view. On the THS actuator, which is an electrohydraulic unit, you've got different components here. Okay, so I'm just going to name them. You don't have to memorize them. I'm not going to put that on the test, but I'm just giving you so you can verbally hear it. But you've got 2 hydraulic valve blocks. You got valve blocks, your transducer packs, you got a gearbox, you got a mechanical input shaft in that actuator. These are all components, okay, of the actuator. You have 2 motors. You got a pitch trim actuator that's part of the THS actuator. That's what I'm talking about right now, is the THS actuator that's moving on the THS, right? Okay, so I just wanted to, again, verbalize some of those components related to the THS actuator. Okay, and the picture gives kind of gives you the relationship of the gearbox, the valve blocks, the ball screw jack and chain, etc. Input shaft, you can see. That way you know where they're located, that in the whole, actuator. Okay, now what about position indicating for the THS? This one here is indicated, on the control wheel on the center pedestal. And you've got an index on a scale that's painted green. So, you got indications there. And this whole thing is still repeated on the FCDC, or on the data concentrator, your FCDC. That's going to be actually on the lower ECAM display unit is where you'll find the same information. Okay, so, touching, I just gave you kind of an overview, giving you familiarity with the actuators and some of the components when we talk about the trimmable horizontal stabilizer actuator. And then kind of, remember I talked about the yaw damper, and mechanical control of the THS, because 2 places where we have mechanical is where? Is rudder and your THS. Okay, so we've covered a lot with going over primary flight controls and, the primary flight controls and the related secondary, namely your spoilers, which would include your speed brake function as well. Being able to control the ground spoilers, or basically the spoilers 2, 3, 4, and all that. So I hope this gave you, a good feeling for, for what we're talking about here with the control computers and kind of the way that they're just gathering that data and taking that, assessing, and then being able to translate that to hydraulic actuation to the end users. And then before we close out session 1, I just wanted to touch on, obviously you have bite checks. You guys are familiar with all that, but I just wanted to verbalize some of this stuff. So the menus that, I've talked about some of these things, but you've got your EFCS, okay, your obviously electrical flight control system maintenance messages, and those are going to be processed through your 1 and 2 sub menus. So I'm on menus. So if there's any maintenance, information, these are your tools, then you're going to be looking for your sub menus, and you've got 2 of them. Remember that 1 or 2, like I mentioned, and they're identical. So, what kind of information are you going to find here? You've got, you have memory, so you've got internal memory, function memory, so that's one of them. and that's to read internal memories. You've got byte data that's there for shop use, and also for, you know, anybody else. If you're trying to switch out or any information about what's there, you know, like about the equipment there, then that information is going to be there. So that's that one. And then you also, of course, have test, right? And then you have a ground scan, LRU identification. You got class 3 faults is another listing on there, and of course you have your leg reports. Those will be part of that as well. So I know that in the last thing I had mentioned, I think it was on landing gear, we talked about you know, how, you know, previous flights, you know, previous legs, you know, how many, and I said 63. Here it's only the failures of the last 64 flights affecting flight controls are displayed. So last 64 flights are going to show up on the previous legs report. And then you have identification of your LRUs, so you'll have some part numbers there. And then ground scan, it's used on the ground, obviously, because you want to see the failures that are existing at the time, you know, at that time. And then troubleshooting data, that's another one that allows to show the fall information and data that's concerning the system status. And that's what's happening before and after. So you know, okay, what can you assess? What was before that seemed a little odd or off, and then, okay, what happened after? So that's your troubleshooting data as part of that. And then this is all presented. You have the test that's presented, the test function, and that's presented on the MICDO by the FDCs. Okay, remember concentrators are giving that data over. Well, in this particular case with test, it's actually sending it to the MICDOs, okay, your multi-purpose control and display unit. Okay, so it's going to display those test results on the MICDO, and then it's going to initiate any tests that are related to, obviously we're on flight controls, so that's what we're talking about. The two that can be done are the ones for elevator and aileron, servo control damping tests. So your damping test for the elevator, for both servo controls, one for the elevator and one for the aileron. Okay, and then just remember I mentioned periodic test earlier. That's what I'm talking about. Those two tests I just mentioned right now are periodic tests. And then you have automatic tests that are built in order to obviously pick up some things that are not obvious. So you've got some failures going on kind of behind the scenes, or, you know, it's going to be those are going to be running those automatic tests to pick those up. And then you have interfaces with what? You know, you're going to have those interfacing with your centralized fault display system, your CFDS. And inputs are connected obviously to the CFDIU, your centralized fault display. So, and then that's just typical with connecting with your, you know, Bayer ERIC 42029. But so all those, just kind of let you know, your ELACs and your SECs are going to be, you know, be detecting the LRU failures. It's constantly monitoring, constantly detecting. So I'm just kind of reiterating right now, kind of summing up this whole session 1, because we've covered a lot of material right now. So just remember that, you know, how many, you know, ELACs do we have in each of the aircraft? 2. How many SECs do we have? 3. You know, FCDCs, we have 2. We have 4 accelerometers. Okay, that's another where you have vertical acceleration values that are being sent to the ELACs, and for, you know, comparing and calculating, etc. To get those any failure signals, those are going to be sent out. It's going to be able to detect and identify and isolate them, and then send them to the ECAM, send them to the CFDUs. So that's the heart of everything here are these control computers. Okay, so this concludes our session 1. And, you know, our next session is going to cover secondary flight controls, and then we have some surfaces there. But, you know, mainly we're talking about flaps and slats, essentially. So there's, you know, we're going to cover all that's related to that in our next session. And we will be going over some knowledge checks. So we will definitely have a review because, again, this sky's the limit as far as the number of test questions that could be, you know, you can be tested on, right, for all this material. So I don't want to make it, you know, such a laboring thing for you. We want to make sure that you can, you know the material, you know, get more than familiar with it. Okay, So we'll get on to that in a little bit. All right, we are now on to session 2. This is our final session on flight controls, and we know we covered primary flight controls earlier. Now we're on to secondary. Okay, that would be your flaps and slats. And again, here you've got control computers as well to operate in conjunction with one another to ensure the functionality of both the flaps, and the slats. So just kind of give you an overview, broad view on what we have here. The aircraft on Airbus has 4 flaps and 10 slats. And so on here, the surfaces are not individually powered like they are with the primary. So here they're operating as a group, as far as the flaps and the slats. You have 2 power control units. You have one for the flaps and one for the slats. And you have 2 computers. Okay, so those are your CFCC1 and CFCC2. Okay, CF stands for slat, flap, and of course control computer. You also have kind of a new term, probably, unless you've been around Airbuses, a pickoff unit. Okay, pickoff units basically is just being able to pick up signals of the out-shaft position of the PCUs in order to then transfer that information. So we do have those, the feedback position and also instrumentation position pickoff unit. Okay, in addition to those types, we have also the asymmetry position pickoff units. Okay, there's also proximity sensors, so we do have those on a interconnecting strut, and those sensors obviously are going to send those signals to stop the flap movement if the strut moves more than a certain limit. With proximity sensors, we also have switches, okay, which are monitored by the landing gear control and indication units, your LGCIU that we talked about in landing gear. So those are, that's what we have there. Okay, so and of course the diagram gives you kind of an orientation where these different parts are different things are located, because we have just kind of a host of things here with the flaps and slats. So for example, we're going to be talking about wingtip. We got wingtip brakes, the actuators, of course, and all that. They operate the same, as you well know. So I want to also introduce the command sense unit. This is installed in the cockpit on a 114 VU panel, and what it's doing is just changing inputs from the control lever into electrical signals and sending them over to those control computers. And then you just kind of have an idea of what it looks like, just kind of a diagram, an illustration of it. Okay, and as far as the actual computers, what are they made of? We talked about the ELACs and SECs. It was talking about subunits within those, like your MON unit and COM unit. Here, as far as what are we talking about? We're talking about the control computers for slats and flaps. We have, the 2 control computers monitoring the flap system. Because it's looking for, remember, these computers are looking for failures, and besides just monitoring, but it is looking for any kind of failures that are going on. And we're going to be talking about the power transmission system, so just a little bit, that there's that, so that there could be something wrong with that. All your LRUs are going to be monitored, your power supplies, of course, your pickup units, valve blocks, power supplies, etc. And then within the power transmission system, you could have a host of things that could go wrong with these components. So you have, half speed, you've got a system jam, low hydraulic pressure, runaway, asymmetry, okay, things like that. There's also, and I know I've mentioned this before, but we're coming back to it, but I mentioned about the angle of attack earlier and how we're talking about limitations. Well, here there's what's called the slat alpha lock, speed bulk, and basically what this is it's going to monitor the control computers are going to be monitoring angle of attack and the airspeed, because this is what this has to do with. And so therefore it's not going to allow the slats to be retracted from one position to another at too low a speed or at too high of an angle of attack. So those are the 2 conditions. Once you have an angle of attack and it's normal because you have angle of attack along with, in conjunction with airspeed, then it's not going to, we're not going to have that retraction going on with the slats. So just so you know, with that hindrance of the, that inhibition of this is it's called the alpha lock. Okay, and you're going to see that on the engine warning display. So, and the other place you're going to see it is also on the ADRU. Okay, so here's kind of the conditions with that. On slat retraction, the only way that's going to be happening is if the alpha is more than 8.5 degrees. Your computed airspeed, your CAS is less than 148 knots. Okay, so those are your limitations there. And also the function resets if alpha decreases below 7.6 degrees, or if the CAS increases, above 154 knots. So again, those are the slat retraction, the conditions where it's not possible that you're going to have the retraction of the slats. And then with the alpha lock, that's not going to be possible if you have the aircraft's on the ground and you have an airspeed that's below 60 knots, or you have the slat retraction is set for below, set before the alpha is more than 8.5 degrees, or CAS is less than 148 knots. So those are conditions for that. Your computers, just like the other, things, we're gonna, it's just receiving signals to be able to operate, obviously, at different things. But, here we have 2 channels with the control computers, and each of them is going to monitor inputs from different control units. One is going to be your landing gear CIU, as well as your ADRU, and also from your CFDIU. Okay. All right. So let's kind of look at some system ground operation inhibit function. Your SGOI, which is system ground operation inhibit, is going to prevent flap system operation when the cargo doors are being operated. Okay, that's what that means. Okay, and then your power control units, these are hydromechanical, and they're going to be supplying that mechanical power to the flap and slat transmission system. There's 2 motors to the PCUs. You have the motors, each of them has a pressure off brake and also a valve block. Okay, and then also you have a differential gearbox that's going to connect the out shafts of the hydraulic motors and then transmitting that torque to the power transmissions for the flaps, or the slat system. Okay, and as far as your LRUs for the PCUs, I'll just get it out so that you can just be aware. But your LRUs in this particular system or unit are going to be your pickoff units. You got your filters. There's 6 solenoid valves, 2 valve blocks. You have 2 hydraulic. I mentioned the 2 hydraulic motors, and the 2 pressure off brakes. Those are your line replaceable units. And the diagram again shows you where things are located in relation to one another. Okay. Now, as far as location of the PCUs, the one for the flap is on the aft main landing gear compartment bulkhead center line, immediately above the PTU. Okay, that's where that's located. And just so you know, the PCUs are the same. The ones used for, the one for the slats and the one for the flaps are identical. But again, do make sure you look at the AMM, and just that's a very important thing to verify. And of course, the hydraulic systems that are coming into play here are going to be the green and the yellow. Now, as far as the slat power control unit, your PCU for this one is mounted on the aircraft center line, and it's at the lower forward bulkhead of the main landing gear compartment. Okay, and as far as the hydraulic supply, for the slat PCU, this is going to be from the green and the blue systems. Okay, and the diagram kind of just shows you the connectors. You have connector A and connector B, and your IPPU. You can see that there, and where the PCU is located. Okay. Now, what about the valve blocks? Your valve blocks, these are, electrically controlled. There's 2 valve blocks per PCU. Okay, here are each of the PCUs, and it's going to control the flow of hydraulic fluid. Okay, and there's also a multi-piston hydraulic motor that receives, or the motors are multi-piston that are going to receive the hydraulic pressure from the valve block. Okay, so from valve block to motor. The output shaft of the motor itself is connected to the pressure off brake. Okay, that's going to lubricate the motor. Of course, you have the cylinders in the motor. Those are connected to 2 ports. You got extend and your retract ports. Okay. And then the other thing you're going to have is, remember I mentioned the LVD transducer earlier. You do have mounted on one of the ends of that valve block a linear variable differential transducer. So you have your LVDT, there, that's monitoring the position of the control valve. That's what that is there mounted for. So opposite of that, okay, on one end of the valve block you have the LVDT, and then on the other end you're going to have 2 directional solenoid valves, and also 1 pressure off brake solenoid valve. Those are where your valves are located. So one end is valves, and the other one's the actual valve block. And so, just giving you orientation there. When you have low speed mode, then the control computers are going to energize those solenoid valves and also the POB solenoid. But when it's in high speed, then it's going to energize the extend solenoid valve and the POB solenoid. Some of the primary components you'll find in the valve block are going to be 5 restrictors, pressure and return ports, your main control valve, electrical connector, of course a filter. Okay, and the diagram gives you an idea of the valve block and kind of an exploded view of the different parts. Okay, now the pressure off brake, I know I mentioned that earlier, so here you've got 2 pressure off brakes per PCU, and they're located between the hydraulic motors and the gearbox. Okay, and you also have, basically when hydraulic pressure is there, it's gonna, we got this chain reaction going on. It's gonna overcome the force of the springs, and then you have friction discs that are there. And held together by the springs, and once they disengage, then they're going to disengage, and then you have the POB that's applied to the hydraulic motors, and then that becomes inoperable to operate. So that's why it's pressure off. Okay. And then just something about the pickoff units. These are position pickoff units. Remember I said there were different ones, but instrumentation, feedback, asymmetry, etc. So with here you have 2 PPUs that are installed in the flat PCU, and those are going to be your instrumentation and your feedback. And then on the transmission system you're going to have the asymmetry PPU. Okay, so your instrumentation and feedback are going to be on the flat PCU, and then your asymmetry PPU is going to be installed in the transmission system. Okay, and always follow the AMM, but in this particular case, these PPUs are interchangeable. Okay, there's nothing inherently different about one that is unique. Okay, that it can't be installed, in any of these places. Okay, and then when you have this going on, there's also a synchro transmitter that's going to send that data, okay, to the control computers. And so there's 2 of them, okay, just like the pairs of sensors I had mentioned before. One of them is going to one computer, and the other one is sending messages to the other computer. So one to CC1, the other one to CC2. And these obviously are going to be showing up on the ECAM display for under the flap slat, for showing flap slat position. And you have that there. The instrumentation, okay, the position pickoff unit, that's the function of that is it's actually monitoring the movement of the mechanical transmission system. Okay. Okay, and then you also have, you know, the manual adjustment on the PPUs. So that's one thing you can do on there. It's a manual adjustment. And the way you're going to do that, you unlock the locking plate. There's a locking plate of the drive shaft, and that, you know, is unlocked. And you just, after that, you want to make sure that that drive shaft can move, you know, to move. And then you want to turn the input shaft and then align the drive gear 0 mark and the orange 0 indicator with the fixed pointers, so to get that all aligned. And then make sure that the input shaft 0 mark and the fixed 0 mark are aligned. And that's making your manual adjustment of that. And there's a diagram showing you the orange indicator, and then there's the fixed pointer and the drive gear 0 mark as well. Okay. All right. Okay, so, you know, instrumentation, again, feedback pick-off unit, are just giving the signals of the output shaft position of the PCU. That's what they're there for. Okay, and, you know, again, sending those messages to the control computers. All right. Now, there's also a T gearbox or transmission system for the slat, and the T gearbox, you know, there's torque shafts and the gearboxes that are going to transmit mechanical power from the PCU to, you know, to the gearboxes of the actuators. Okay, so eventually we're going to the actuators. So that's what it's doing. And then those gearboxes, you know, transmit the power through the torque limiters to the actuators. That's what it does. Okay. And the gearboxes are, so you're aware, they are filled with grease. And of course there's seals there to prevent, you know, just to protect the, you know, to protect that box. Okay. And you have inspection plugs on that, by the way. Okay, so, you know, back on, you know, transmission system for slats. You've got the gearbox, you know, obviously. And then you have also in each wing are 2 types of actuators of different sizes. Okay, and the larger diameter actuators at tracks 2 and 3 included more gearing than the other actuators, so 2 and 3 are larger. Okay, and of course you have lubrication with the grease in there. Okay, now a little bit on the tracks, because you have slat tracks. Obviously these things run on a track for movement and whatnot. So here you've got each of the 5, you know, we got 5 slat surfaces per wing, and those are, you know, obviously in the tracks. And you got the roller installed in there. That's standard, is you have rollers there in those tracks to ensure that you have movement, right, of those surfaces. So you have that, and then of course they're displaced by the action. You have a rack and pinion drive that's making that all happen. Okay, all right, so of course you have different dimensions for that. And torque limiters, you do have those that are just going to control the transmission of the torque from the gearboxes to keep the torque, right, within a certain limit. So you don't want to have an overload, you know, overdoing on the mechanical part of the actuators. So you do have those torque limiters. And so each input gearbox has a torque limiter. Okay. And I just wanted to, you know, point out the diagram shows you, you know, what the torque limiters look like. You got your ball ramp input members, the indicator lever, as well as a pin, and you get your input, of course, and your springs. Okay, what about the asymmetry position pickoff unit? Those are located at the very end of the slat torque shafts, and of course they're going to be picking up on the position and speed of the slats, and that information, of course, is going to those computers. Okay, and it's just a picture kind of showing you, you know, where it's located, you know, at the end, at the tip of the wing, and then a blowout of it. Okay, and what about the flap? That was our slats. The flap actuator, there's two. Okay, and you have actuator 1's installed on track beam 1, and the actuators 2, 3, and 4 are installed on the rear spar. Okay, so you have those there, and the shafts and gearboxes in the fuselage and the wing are going to be transmitting that mechanical power to the PCUs, to the actuators. Okay, it's same situation. All right. Okay, and again, just showing the flap torque limiters, just kind of a blowout of that. Okay, and then of course you have your link arms. You've got the bolts attach the flap link arms to the flap bottom surface. You also have a shear pin. So when the flaps are deployed to a certain position, where the levers and link arms are aligned, then the torque limiters are they're not operable. Okay, and just be aware of the shear pins. Those, you have covers, because shear pins can get bent and distorted. So, if there's anything to be looking for, it's the shear pins not being not being distorted in any way. Okay, and you can see the blowout of the different pieces, the different parts to the link arms. Okay, and you also have flap carriages, just to mention that. So you have those. There's vertical load rollers and your side load rollers that keep the carriages, right on the tracks. Then you have wing check brakes. The wingtip brakes are there. Of course, they're at the tips of the wings, and the brake is normally just running and allowing just normal operation. Okay. And so, of course, they're going to stop if the control computer's, sending signal, or that there's something wrong. There's some kind of failure. Okay, and kind of the picture gives you a blowout. And it shows you, where the solenoid is located, and your hydraulic manifold, and all that for the tip brakes. You have the same thing with these slats. So you've got two slat wingtip brakes that are located in the wing leading edge, and that's going to be after the number 5 slat on each wing. Okay, and there's panels that you can get to that are access panels for getting there. Okay. Okay. All right, and kind of just a little bit on just kind of the mechanical. I mean, this is mechanical and electrical. So it comes to operating the flaps and slats. That's what we have, with it. I know I mentioned the interconnect strut earlier. Just to understand, because it's really the same in in the other aircraft as well. So it's just so basically you have this interconnecting strut, and it's basically connecting, the inboard and the outboard flaps. And there's a flap attachment failure detection sensors that are there to monitor, the flaps for a position difference that's outside of certain limits, to not be too much. But you definitely have the interconnect strut. Okay. All right, so interconnect strut, and then we also have, of course, the indications on the ECAM, the EIS, that's going to show the position of the flaps on the upper display. So, flap slat indication, what are we going to have on here? We got slat visual indication, and then we have flap visual position markings. Okay, and as far as another indication, you have a gray symbol that shows the fixed center section of the wing. So gray symbols just showing the fixed center, green indications are showing the correct position of the slats and flaps. So green's always a good color. Okay, that means everything's good. Okay, All right, some of the things you might see that's going to be a caution is the message S locked or F locked. Okay, that's for your slat locked and flap locked. That's going to appear in amber. So that's just a caution. You know, that's a caution, and that's going to be with an associated ECAM caution. And when is that going to show up? That's going to be when the wingtip brakes are applied, or when there's a, you know, there's no alignment between the two flaps. Then those are going to show up on there. And then there's the A-lock. Remember, A-lock is short for alpha lock. So if you see A-lock, it's the same as alpha lock, and you know, alpha lock, alpha speed lock. And that's a message in itself that can show up in blue. If blue is good, it just means it's active. Okay. Okay, and there's, you know, you can see the pictures on that. Okay, now the extend flaps or slats, extend flaps and slats, you know, you have that. And you know, as far as the circuit breakers, because you know, that's important to know, right? If anything here, it's, you know, where are the circuit breakers? What are you going to do with the circuit breakers? So if you're going to extend the flaps without extending the other, you know, the slats, then you want to look at the circuit breakers, and you're going to pull some things. So this is a configuration here. You know, look at your AMM, because you know, some things might have changed, but just letting you know, there's on the circuit breakers, that's where you can, you know, choose either flaps only or slats only, and being able to extend them. Okay. All right. So again, there's mainly just kind of getting familiar with what the indications that you have in the cockpit, and then knowing, you know, there's an interconnect strut, which is pretty standard, connecting the two sides, and you know where that's located, because you have the outboard flap, and that's where you have that interconnecting strut. Okay. Then you have your proximity sensors, of course, like I mentioned before. So I'm just kind of summarizing here what we've gone over. Of course, the interconnect strut, you know, just to kind of enhance a little bit more on that, it's going to allow the inner and the outer flaps to run independently, you know, within a certain limit. So that's what you have that there for, and it's going to obviously be still sending data to the control computer when you have that movement going on with the inner, you know, and the outer flaps. Of course, if it goes outside of certain limits. So you have that. You do have the kind of mechanical electrical control that's going on with the operation of the slat and flap control lever, okay, which is mechanical. And then you've got, you know, the CSU, which is your command sense unit, that's going to, right, it's going to transfer that into electrical. Okay, okay. So, giving you an idea about, you know, about what, you know, we're talking about here with the wing, with the flaps and slats, and the control computers that are involved. And you know, they still run on tracks. If you worked on planes, you know, you've got rollers, you got tracks, you got flap carriages. I mean, you just want to make sure those, you know, the shear pins are not bent, or you know, something, you know, or corrosion, you know, things like that that can become a potential problem. Just, you know, obviously visually inspect and you know, just do your due diligence with all of that. Pick-off units, you know, being able to, you know, detect position and being able to transfer that over to control computers. Okay, so that pretty much covers session 2. As far as test questions that are going to come from here, and we are going to do a review of this, is, you know, locations, you know, for some of this, and then just know the circuit breakers. I'm not going to give specification on the exact, you know, as far as what's on the circuit breaker, because again, that may be a little bit different, and I don't want to confuse you with naming to something so specific that's on a circuit breaker. So I'm leaving that out. But do be familiar with, you know, the position pickoff units, and some of the messages, some of the fail messages that would show up on the ECAM. Okay. All right, so we'll go ahead and conclude with this, and then we're going to go on to some knowledge checks so that we can prepare for this test, and then go over, again, just review it, and then we'll go over some knowledge checks. All right, let's go ahead with going over some of the knowledge checks. I hope you have your handout out so you can follow along. And we're gonna, it's not that lengthy. Again, I could give questions, numerous questions, but I just want to have you familiar with some of this stuff. Question number 1, what 2 subsystems are part of the electrical flight control system? Is it option A, FCDC and SEC, or the FCDC and ELAC? The answer is A, the first one. Question number 2, which flight control device does the SEC control when in standby mode? Is it pitch control devices or your spoilers? Okay, the answer is the first one. Number 3, how many ELACs and SECs are there on each aircraft respectively? Your first choice, 3 and 3, or is it 2 and 3? The answer is the second answer. Number 4, the COM and MON units are part of the CLAC and ELAC. Is that true or false? That's true. Number 5, where are the ELACs located? Option A, 83 and 93 VU panels, or is it 83 and 84 VU panels? That's going to be option B. Number 6, where are all the SECs located? Option A, 83, 84, and 93 VU panels, or 83 and 84 VU panels? Okay, that answers the first answer. Number 7, the EFCS is a centralized system that provides access to FCDC status and failure information. Is that true or false? That's actually false. Number 8, information gets transferred from the FCDC to the ECAM. What kind of information is transferred? Here are your 2 choices. Okay, first choice, failure signals and actuator information, or is it option B, the position and availability of flight control surfaces and failure signals? Okay, the answer is the second one. Okay, position and availability of flight control surfaces and failure signals. Number 9, what are the sources of power for the flight controls? Is it option A, the green and blue hydraulic systems, or is it green, yellow, and blue hydraulic systems? Okay, the answer is the second choice. It is all 3. Number 10, what is the function of the rudder? Is it for yaw control or pitch control? The answer is the first one. Okay, I mentioned that, yaw. Number 11, to which type of flight control is the accelerometer related? Is it related to option A, which is roll control, or related to option B, pitch control? Okay, the answer is the second one, pitch control. Number 12, what is a load cell? Okay, option A, detects buckling of the rod that's generated by the load from the rudders, or is it a cell that is loaded with hydraulic fluid for the hydraulic actuators? Okay, the answer is the first one. It detects buckling of the rod that's generated by the load from the rudders. All right, number 13, how many servo controls are there for each of the ailerons? Is it 4 or 2? Okay, the answer is 2. Okay, now this session 2 questions. Number 14, how many total flaps and slats does the Airbus A320 family aircraft have? Is it 4 and 10 respectively, or 5 and 10 respectively? Okay, the answer is the first one. Number 15, what is the function of the command sense unit? Is it option A, to change input from the side stick controller into digital signals? Or is it option B, to change input from the control lever into electrical signals? Okay, the answer is the second choice. Number 16, where is the PCU for the flaps located? Are they under the wings, or option B, aft main landing gear compartment bulkhead? Okay, it's the second choice. Number 17, where's the PCU for the slats located? Option A, on aircraft centerline at the lower forward bulkhead of the main landing gear compartment, or option B, in the cargo compartment. Okay, that answer is number 1, the first answer. Number 18, and this is our last question. What do the APPUs do? In case you forgot what that was, it's asymmetry position pickoff units. Option A, they give data of slat position and speed and send it to the control computers in order to find asymmetry between the left and right wings. Or is it B, they give data of slat position only and then send that information to the Sec 1 computer? Okay, the answer is the first one. All right, so if you've written down the answers, you're doing pretty good. So that's a good preparation for taking the test. All right, that'll be all for the knowledge checks on flight controls. And thank you for participating, by the way. And if you have any questions, certainly email us and we'll help you out.